What if most of the universe is made up of something we cannot see or fully understand? Dark energy and dark matter, elusive forces that control the cosmos, remain among the greatest mysteries that challenge our understanding of reality. But within these forces lies objects so unimaginably strange that scientists still don't know what they are. Join us as we delve into the biggest mysteries in the universe. The enigmatic dark energy. Dark energy is a mysterious force that plays a crucial role in the expansion of the universe. To understand it, picture the universe as a balloon being inflated. As the balloon expands, sections of it move away from each other. Dark energy is thought to be the driving force behind this acceleration, pushing galaxies apart at an ever-increasing rate. The discovery of dark energy began in the late 1990s when astronomers were studying supernovae, which are the explosive deaths of certain stars. These astronomers, studying light from these distant explosions, expected to see all galaxies slowing down as gravity pulled them together. However, they found something surprising. The further they looked, the faster those galaxies seemed to be moving away. This unexpected observation prompted scientists to propose the existence of dark energy. It was a radical idea suggesting that not only did space itself expand, but it was doing so at an accelerated pace due to this unseen force. Since then, dark energy has become a fundamental component of modern cosmological theories, although its exact nature remains one of the great mysteries in science today. Dark energy and dark matter are two mysterious components of our universe, but they serve very different roles. Dark matter acts like an invisible glue, holding galaxies and galaxy clusters together. Imagine trying to keep a group of stars in a friendship circle. Dark matter provides the gravitational pull that prevents these stars from drifting apart. Even though we can't see it directly, scientists have observed its effects by measuring the way light bends around massive objects and tracking the movements of galaxies, which indicates that there's more mass present than we can observe. On the other hand, dark energy is a force working against gravity. Think of it as an unseen hand pushing galaxies apart, contributing to the universe's rapid expansion. While we perceive this expansion as galaxies moving away from each other, dark energy continues to gain importance over time, influencing the cosmos on a much larger scale. It's as if the universe is filled with a repulsive power, causing it to stretch and expand, almost like a balloon inflating. In short, dark matter pulls things together, creating structure in the universe, while dark energy pushes things apart, driving the expansion. Understanding these two elements is crucial for grasping how our universe functions and evolves. Each plays a unique and vital role in shaping the cosmos as we know it. Dark energy plays a crucial role in the way our universe is expanding. To understand its influence, visualize the universe as a stretching balloon. As the balloon inflates, the surface expands, and this illustrates how galaxies are moving away from each other. Initially, it might seem that gravity, the attractive force between masses, would slow down this expansion. However, dark energy acts like a repulsive force that accelerates this process. Imagine that as the universe expands, dark energy fills the space. Its properties push against the pull of gravity, leading to a situation where the expansion doesn't just continue, it speeds up over time. This means that not only is the universe getting larger, but it is doing so at an increasing pace. The more we learn about dark energy, the more we realize how mysterious it is. It makes up a significant portion of the universe, yet we cannot directly observe or measure it. Scientists have inferred its presence through observations of distant supernovae and the large-scale structure of the universe, which show that distant galaxies are moving away from us faster than we would expect, based solely on gravity. As researchers explore this cosmic phenomenon, they are faced with many questions. Why is dark energy causing this rapid expansion? How does it interact with the other forms of matter and energy in the universe? Each discovery leads to a deeper understanding of the universe itself, shaping our view of its past, present, and future. The dance between dark energy and the cosmos continues to be one of the most exciting frontiers of modern astrophysics. Dark energy is one of the most intriguing mysteries of the universe. It makes up a significant portion of all energy in the cosmos, and its exact nature remains elusive. One of the leading theories proposes that dark energy is a property of space itself. As the universe expands, new space comes into existence, and this space could have an energy density that exerts a repulsive force, pushing objects apart. Another theory is linked to the idea of a constant force, often referred to as a cosmological constant. This concept suggests that dark energy has a uniform energy density, filling space evenly, regardless of the expansion of the universe. Think of it like a balloon that inflates. No matter how big the balloon grows, the surface tension feels the same throughout, suggesting that dark energy continues to act consistently as the universe expands. There are also theories related to dynamic fields known as quintessence. This idea posits that dark energy is not constant, but rather a field that changes over time. Just like the weather can shift, so too could the characteristics of dark energy, influencing how quickly the universe expands at different points in its history.
Lastly, some researchers are probing the possibility of modifications to our current understanding of gravity. In this scenario, dark energy might emerge from alterations in gravitational laws on cosmological scales. Essentially, this means that what we perceive as dark energy could be the result of gravity behaving differently when looking at the universe as a whole.
As scientists gather more data, these theories continue to be refined, paving the way for a deeper understanding of the enigmatic force driving the universe's accelerated expansion. Each theory presents unique implications for the future of the cosmos, and ongoing research may eventually unravel the true nature of dark energy. Scientists measure the effects of dark energy on cosmic structures by observing how galaxies and clusters of galaxies behave over time. Dark energy is a mysterious force that is thought to be driving the accelerated expansion of the universe. To understand its influence, researchers look at the large-scale structure of the cosmos, how galaxies are distributed, and how they move apart. One fundamental approach involves studying distant galaxies. As light from these galaxies travels towards us, it carries information about their existence billions of years ago. By comparing the position and brightness of these distant galaxies to those that are nearer, scientists can determine how the expansion of the universe has changed over time. They also measure the light from supernovae, which are exploding stars. These supernovae can serve as standard candles because they have a known brightness. By examining how bright these explosions appear from Earth, researchers can calculate their distance. When they analyze these distances in conjunction with redshift, the shift of light to longer, less energetic wavelengths due to the expansion of space, they can infer how quickly the universe is expanding and how dark energy influences this rate. Additionally, scientists utilize gravitational lensing, where massive objects like galaxy clusters bend light from more distant objects. This bending reveals how much mass exists in those galaxy clusters and how the expansion of the universe affects the arrangement of matter. By studying the patterns of lensing, researchers can further probe the role of dark energy. All these methods combine to create a fuller picture of the cosmic environment. Each measurement helps build a clearer understanding of how dark energy impacts the universe's fate and its large-scale structures, guiding scientists in figuring out one of the cosmos's greatest mysteries. Dark energy is a mysterious force that plays a crucial role in shaping the future of our universe. Imagine the universe as a balloon being inflated. At first, the expansion of this balloon was slow, but as time went on, something unusual happened. The expansion started to speed up. This acceleration is attributed to dark energy. Dark energy acts like an invisible hand, pushing galaxies apart, causing them to move away from each other at an increasing rate. Scientists believe that it makes up a significant portion of the universe, more than regular matter and energy combined. As we look into the far future, the effect of dark energy becomes even more pronounced. If this acceleration continues, galaxies will drift farther apart, and eventually distant galaxies may become invisible, as their light will take longer to reach us than the expansion of space. Over time, this could lead to a scenario often referred to as the Big Freeze. In this distant future, the universe could become a cold, dark, and empty place, with stars running out of fuel and galaxies disappearing from sight. Stars would burn out, leaving behind black holes or neutron stars, and the overall temperature of the universe would drop significantly. This outcome raises profound questions about the ultimate fate of everything we see around us. Dark energy, therefore, is not just a scientific curiosity, it is a central player in the story of the universe's evolution, influencing its vast future in ways we are only beginning to understand. The study of distant supernovae is a key tool for scientists trying to unravel the mystery of dark energy, the force believed to be driving the accelerated expansion of the universe. Supernovae are explosive events marking the end of a star's life. Among them, a specific type called Type A supernovae is particularly valuable. These explosions occur in binary star systems, where one star siphons material from its companion until it reaches a critical point and detonates. Because Type A supernovae have a consistent peak brightness, they act like cosmic beacons. By measuring how bright these supernovae appear from Earth, scientists can gauge how far away they are, similar to how a lighthouse's light can indicate its distance based on brightness. When astronomers observe distant supernovae, they find that these explosions are fainter than expected if the universe was simply slowing down or expanding steadily. Instead, their dimness suggests that the universe is expanding at an accelerating rate. This unexpected acceleration implies that something is pushing galaxies apart, which is where dark energy comes in. By mapping the light from numerous supernovae across time, scientists can create a detailed picture of the universe's expansion history. This research helps to confirm that dark energy constitutes a significant portion of the universe's total energy content, influencing its fate and structure. Ultimately, studying distant supernovae provides critical evidence about how our universe is changing, shedding light on one of the most profound mysteries in modern astrophysics. The cosmic microwave background, or CMB, serves as a crucial piece of the puzzle in understanding dark energy. Think of the CMB as the afterglow of the Big Bang, a faint radiation filling the universe that provides a snapshot of the cosmos when it was just a few 100,000 years old. By studying this ancient light, scientists can learn a lot about the universe's early conditions and its overall structure. When researchers measure the CMB, they look at tiny temperature fluctuations across the sky. These fluctuations reflect the density variations in the early universe, which ultimately shaped how galaxies formed and evolved. By analyzing these patterns, scientists can determine the amount of ordinary matter, and dark energy that exists in the universe. Dark energy is the mysterious force driving the accelerated expansion of the universe. The CMB measurements help establish the universe's geometry and its overall density. If the universe's density is below a certain point, models suggest that it must be dominated by dark energy, which counteracts gravity and pushes everything apart. Thus, CMB research not only highlights the universe's history, but also provides essential data that informs theories about the nature of dark energy. The cosmic microwave background is not just a relic of the past, it's a tool that unlocks the mysteries of how our universe is expanding and the role that dark energy plays in that process. Dark energy poses one of the most significant puzzles in contemporary physics and cosmology. At its core, dark energy is an unknown force that makes up a large part of our universe, pushing galaxies apart at an accelerating rate. This phenomenon directly challenges our understanding of gravity. We typically think of gravity as a force that attracts objects, pulling them closer together. However, dark energy appears to work in the opposite manner, driving them apart. The existence of dark energy forces scientists reconsider their theories about the universe's composition and evolution. Traditional ideas suggested that gravity should slow the expansion of the universe by pulling galaxies towards each other. The observed acceleration of this expansion indicates that something fundamental is missing in those theories. Furthermore, The nature of dark energy remains elusive. It does not fit neatly into the categories of matter or energy we know about. While we can detect its effects through the movement of galaxies, we have yet to identify what it actually is. This unknown factor leads to ongoing debates and research, pushing scientists to explore new models and ideas, such as the possibility that our understanding of gravity itself may need revision. Some physicists are even investigating the idea that dark energy might be a property of space itself, rather than a form of matter. This challenges the very fabric of how we conceptualize the universe. As researchers uncover more about dark energy, they may need to rethink not only the makeup of the cosmos, but also the fundamental laws of physics as we know them. Each discovery pushes the boundaries of our understanding, urging us to explore further into the mysteries of the universe.
Exploring dark energy presents us with a range of technological challenges that researchers must overcome to deepen our understanding of this mysterious force. Dark energy is believed to make up a significant portion of the universe, but remains largely invisible and undetectable with current tools. One major challenge lies in the sensitivity of our instruments. Detecting the subtle effects of dark energy requires advanced telescopes and detectors that can measure minute changes in the universe's expansion rate and its structure over vast distances. Another hurdle is the sheer scale of the observations needed. The universe is vast beyond imagination, and gathering enough data from a wide array of angles and distances requires powerful technology and significant time investment. Advanced satellites and space missions need to be developed to get above the atmospheric distortions that can interfere with our observations.
Furthermore, data processing is a considerable challenge. The amount of information collected from observations is immense, and sifting through this data to find relevant patterns related to dark energy requires sophisticated algorithms and supercomputers. Lastly, there's the uncertainty factor. Dark energy acts in ways that are still not fully understood, meaning that creating experiments and missions is complex. Designing equipment that can adapt to unforeseen results or unexpected findings in our research is crucial. These technological challenges highlight the frontier of modern cosmology and the ongoing quest to unravel the secrets of the universe. The mystery of dark matter. Dark matter is a mysterious substance that makes up a significant part of the universe, yet it remains invisible to our current instruments. Imagine trying to understand a puzzle with many missing pieces. Dark matter addresses those gaps in our understanding of the cosmos. Though we cannot see it directly, scientists infer its presence through its effects on visible matter, such as galaxies and clusters in the universe. To comprehend why dark matter is fundamental, we can start with how galaxies form and move. When we observe galaxies, we see they are rotating at speeds that should send them flying apart if only regular matter were present. However, they stay together, suggesting something unseen is exerting additional gravitational pull. This unseen force is attributed to dark matter. In simple terms, think of it as the scaffolding that holds galaxies together, allowing them to evolve and give rise to the complex structures we see today. Furthermore, dark matter plays a crucial role in the overall shape and expansion of the universe. During the early moments after the Big Bang, dark matter helped pull matter together, leading to the formation of galaxies and galaxy clusters. Without this gravitational influence, the universe we know would look vastly different. The existence of dark matter, then, is integral to understanding how cosmic structures came to be and continue to evolve. As researchers delve deeper into this elusive material, they are piecing together the workings of the universe, revealing a deeper story about its origin, structure, and destiny. This ongoing investigation stands as a testament to our quest to understand not just what is visible, but the profound mysteries that lie beyond our sight. The story of dark matter begins in the early decades of the 20th century, when astronomers began to notice something strange in the movements of galaxies. They expected to see a certain pattern in how these galaxies rotated, influenced by their visible mass, like stars and gas. However, they found that some galaxies spun much faster than they should, if only visible matter were taken into account. This discrepancy prompted scientists to wonder if there was something else at play, something they could not see. To understand this, consider a carousel. As the horse moves closer to the edge, it spins faster. If you were watching from a distance and only counted the visible horses, you would assume they were balanced perfectly. But if you noticed that they were moving far too quickly for the number of horses you could see, you might suspect an invisible force was at work, pulling them along. The term dark matter was introduced in the 1930s when an astronomer named Fritz Zwicky studied galaxy clusters. He observed that the mass of visible galaxies in the clusters was not enough to account for the gravitational pull needed to hold them together. His findings suggested that there was a significant amount of invisible mass, which he called dunkle materie, or dark matter. Yet, dark matter remained elusive. It was only through subsequent research that further evidence piled up. For example, studies of cosmic microwave background radiation and afterglow from the Big Bang revealed subtle patterns that provided clues about the universe's composition. Today, scientists estimate that dark matter constitutes a large portion of the universe, though it neither emits nor absorbs light, making it incredibly difficult to detect with conventional methods. Even in present times, we have yet to observe dark matter directly, but its presence can be inferred through its gravitational effects on visible matter. For instance, the way galaxies bend light from objects behind them, a phenomenon known as gravitational lensing, provides strong indirect evidence of dark matter's existence. The quest to understand dark matter continues as researchers around the world work to unlock its many mysteries. Dark matter is a mysterious component of the universe, making up a large part of its total mass. Scientists are still trying to figure out what it really is, but there are several leading candidates for the particles that could make up dark matter. One of the main contenders is called a weakly interacting massive particle, often shortened to WIMP. Imagine a particle that is heavy enough to have a significant gravitational effect, but interacts very weakly with regular matter. This means it could pass through objects including stars and planets without any notice. WIMPs are appealing because they fit into existing theories of particle physics and might be detected through their rare interactions. Another potential candidate is an axion. Axions are hypothetical particles that are incredibly light and represent a theoretical solution to problems in particle physics. If they exist, they could form a type of dark matter known as cold dark matter, which behaves in a particular way to help explain how galaxies form and move. There are also sterile neutrinos, which are a heavier form of neutrinos that do not interact with regular matter in the same way that typical neutrinos do. They could provide the necessary mass and behavior to fit the models of dark matter. Finally, there are theories around modified gravity, which consider that the effects attributed to dark matter might actually stem from alterations to our understanding of gravity, rather than the existence of unseen particles. This view suggests that the universe behaves differently at large scales than we think. While all these candidates are intriguing, researchers are actively conducting experiments to search for direct evidence. The search for dark matter particles continues to thrill scientists, as uncovering their identity could lead to a deeper understanding of the universe itself. Gravitational lensing is a fascinating phenomenon where massive objects like galaxies or clusters of galaxies bend the light from distant objects behind them. This bending occurs because of the strong gravitational fields created by the mass of the foreground object, much like how a glass lens focuses light. When scientists observe this effect, they can gather information about both the object causing the lensing and the background objects. As light travels towards us from a distant galaxy, if it passes near a massive galaxy cluster, that cluster's gravity warps the space around it. This warping causes the light to follow a curved path, which can lead to distorted or magnified images of the background galaxy. By studying these images, researchers can map the distribution of mass within the foreground cluster, including both visible stars and galaxies, and the invisible dark matter. Dark matter does not emit, absorb, or reflect light, making it undetectable directly. However, its presence is inferred through its gravitational effects. Gravitational lensing gives us a crucial tool because the amount of bending depends on the total mass of the lensing object, including both visible matter and dark matter. By analyzing how light bends around these cosmic structures, scientists can estimate how much dark matter is present, even though we can't see it. This technique allows astronomers to create detailed maps of dark matter's distribution in the universe. It highlights the locations and structures of dark matter across vast distances, revealing that it does not clump together in a way that would mirror visible matter. Instead, it tends to take on a more diffuse, spread-out form. This has profound implications for our understanding of the universe, as it not only confirms the existence of dark matter, but also helps us understand how it interacts with visible matter, influencing galaxy formation and the large-scale structure of the cosmos. Dark matter is an invisible substance that plays a crucial role in shaping our universe, especially the formation and behavior of galaxies. Think of dark matter as the scaffolding that holds together the large structures we see in space, while ordinary matter, the stuff we can see like stars, planets, and gas, can be thought of as the building blocks of a galaxy. Dark matter provides the framework within which these building blocks gather and grow. When galaxies begin to form, they require a gravitational pull to attract ordinary matter. Here is where dark matter comes into play. It is present in vast amounts and creates a significant gravitational influence. This allows gas and dust to clump together and start forming stars. Without dark matter, galaxies would not have the necessary mass to hold onto their gas and retain it long enough for stars to form efficiently. Additionally, dark matter affects how galaxies move and interact with one another. Imagine a galaxy moving through the universe like a boat on water. Its path is influenced not just by the visible waves, but also by the underwater currents, which represent the gravitational effects of dark matter. This hidden mass helps to determine the rotation speeds of galaxies, often making them spin faster than would be expected based solely on their visible content. Moreover, dark matter is believed to form large halos around galaxies, acting like an invisible cocoon. This halo slows down the escape of gas and dust, allowing conditions for star formation to last longer. However, these halos also play a role in gravitational interactions between galaxies. When two galaxies meet, the dark matter component can dictate how they merge or interact, often resulting in new structures or even triggering bursts of star formation. Dark matter is essential for the stability, structure, and evolution of galaxies. It sets the stage for their formation, influences how they interact with each other, and ensures that they maintain their integrity, shaping the cosmic landscape we observe today. Without dark matter, the universe would be a much different place, lacking the rich tapestry of galaxies that we see scattered across the night sky. Detecting dark matter directly is one of the most significant challenges in modern physics, as this mysterious substance makes up about 27% of the universe, yet does not emit light or energy that we can observe directly. Currently, there are several experiments meticulously designed to uncover the secrets of dark matter. One approach involves detecting weakly interacting massive particles, or WIMPs, which are a leading candidate for dark matter. Experiments such as the Large Hadron Collider have a role in exploring these particles when conditions recreate the high energies of the early universe. Meanwhile, underground laboratories, shielded from cosmic rays and other interference, host detectors like the LOX-Ziplin experiment. These setups aim to capture the rare interaction between dark matter particles and normal matter, using sophisticated technologies that are extremely sensitive to the faintest signals. Another promising strategy utilizes cryogenic dark matter searches. These detectors cool materials to very low temperatures, making them less susceptible to noise from other particles. By observing minute energy changes when a dark matter particle collides with an atom in the detector, scientists hope to collect clear evidence of dark matter. Additionally, some researchers are exploring other types of theoretical particles, such as axions, which might account for dark matter. Experiments like the Axion Dark Matter experiment are set up to search for these particles by employing strong magnetic fields and highly sensitive equipment to detect any faint signals that these elusive particles may create. While these endeavors involve complex technology and innovative techniques, the heart of their efforts remains grounded in a fundamental curiosity about the universe. Each experiment provides pieces of a larger puzzle as scientists strive to illuminate the shadows cast by dark matter and enhance our understanding of the cosmos. Dark matter plays a crucial role in shaping the universe's structure on a grand scale. Consider it as a hidden framework that influences how galaxies and clusters of galaxies form and organize themselves. Unlike ordinary matter, which makes up the stars, planets, and all visible objects, dark matter cannot be observed directly. Instead, we detect its presence through its gravitational effects. As the universe expanded after the Big Bang, tiny fluctuations in density helped form the first seeds of structure. Dark matter, which is much more abundant than ordinary matter, began to clump together under its own gravity. This clumping created a sort of scaffolding that helped gather regular matter, allowing galaxies to coalesce and grow. Imagine a net with large knots spaced throughout it. The knots represent areas of higher dark matter concentration. Ordinary matter is drawn toward these knots, creating galaxies in the process. This gravitational pull is what leads to the formation of vast cosmic structures, such as galaxy clusters and superclusters, which are essentially groups of galaxies bound together. Furthermore, the distribution of dark matter influences the movement of galaxies. Galaxies are not randomly scattered. Instead, they align along specific paths that reflect the underlying dark matter structure. This creates filaments and voids in the cosmic web, the vast network of galaxies throughout the universe. The areas where dark matter is denser are where we find more galaxies, while large empty spaces or voids occur where there is less. Dark matter acts like a cosmic glue, organizing the universe's structure and dictating the formation and movement of galaxies over billions of years. By understanding dark matter, we gain insights into the history and evolution of the cosmos itself. Researchers distinguish between dark matter and ordinary matter by observing how each interacts with light and gravity. Ordinary matter, which makes up stars, planets, and everything we see around us, emits, absorbs, and reflects light. This means it can be detected using telescopes and other instruments that measure electromagnetic radiation. In contrast, dark matter does not interact with light in any detectable way. It neither emits nor reflects light, making it completely invisible to traditional observational tools. Scientists suspect dark matter is out there because of its gravitational effects on visible matter. For example, when astronomers study galaxies, they notice that the stars on the outskirts revolve around the galaxy at speeds that would cause them to fly away if only visible matter were present. However, they stay tightly bound, indicating an unseen mass, dark matter, providing the necessary gravitational pull. To further differentiate between these two types of matter, researchers also look for the gravitational influence of dark matter in galaxy clusters. Here, the motion of galaxies can be analyzed as they move within a cluster, revealing that there's more mass at play than what we can see. Additionally, studying the cosmic microwave background, the faint afterglow of the Big Bang, offers clues about the existence and distribution of dark matter in the early universe. By combining these observations of gravitational effect with the dynamics of ordinary matter, researchers can piece together the makeup of the universe. This multifaceted approach ultimately helps to reveal the elusive nature of dark matter, showing us that while it may be invisible, its influence is a fundamental component of the cosmic landscape. Dark matter is one of the most intriguing mysteries in astronomy, although it cannot be observed directly because it does not emit light or any form of electromagnetic radiation. Scientists infer its presence through its gravitational effects on visible matter, such as stars and galaxies. Understanding dark matter is vital as it constitutes a significant portion of the total mass of the universe. As we delve deeper into the cosmos, the implications of dark matter for future discoveries are profound. First, dark matter fundamentally shapes the structure and formation of galaxies. By influencing how galaxies are distributed, it helps define the large-scale architecture of the universe. Future studies may reveal new types of galaxies, or even previously undetected ones, which could change our understanding of both galaxy evolution and the universe's history. Additionally, dark matter affects the movement of galaxies. By studying how galaxies move, scientists can indirectly measure dark matter's influence. This pathway may lead to insights about the nature of dark matter itself. Is it made up of unknown particles or other exotic forms of matter? Each discovery could narrow down the possibilities, providing clues that propel physics toward a more comprehensive theory of matter. Moreover, upcoming telescopes and observational technologies aim to probe areas of space that were previously beyond our reach. As we observe more distant galaxies and structures, collecting data about their movements and interactions could yield evidence of dark matter's role on an even larger cosmic scale. The implications of dark matter extend beyond mere mystery. They are a gateway to understanding the universe in new and deeper ways. As researchers work to unravel this enigma, future astronomical discoveries may illuminate not only the nature of dark matter, but also fundamental questions about the origins and fate of the cosmos itself. Understanding dark matter is essential for grasping the overall mass of the universe, because it plays a significant role in the structure and formation of galaxies. To put it simply, dark matter is a mysterious substance that does not emit, absorb, or reflect light, making it invisible to traditional telescopes. However, we know it exists because of the gravitational effects it has on visible matter. Imagine the universe as a cosmic web, where galaxies are like nodes connected by strands of gravitational forces. When we observe galaxies, we see stars and gas, but we also notice that these galaxies rotate at speeds that should cause them to fly apart if only the visible matter were present. This unexpected behavior indicates that there's more mass at play, mass that we cannot see. By studying how galaxies gravitate towards each other and how light bends around massive objects, scientists can infer the presence of dark matter. Essentially, it's like trying to feel the wind. We can't see it, but we can certainly feel its impact. Scientists estimate that dark matter constitutes a significant portion of the universe's total mass, much more than the ordinary matter we can detect. The study of dark matter is not just about filling in the gaps. It fundamentally shapes our models of the universe's evolution. Without dark matter, our understanding of cosmic history would be vastly incomplete, causing the current theories of galaxy formation and large-scale structure to fall apart. This invisible component helps explain why the universe behaves the way it does, pointing us toward a richer understanding of existence itself. As researchers continue to explore this elusive matter, they are piecing together the puzzle of the universe's true composition. The puzzling nature of black holes. Black holes are some of the most fascinating and mysterious objects in the universe, forming from the remnants of massive stars. When a star exhausts its nuclear fuel, it can no longer hold up against its own gravity. This leads to a dramatic collapse, creating a dense core. If the star is heavy enough, this core collapses further until it creates a black hole, an area of space where gravity is so strong that nothing, not even light, can escape from it. The forming of a black hole begins with the life cycle of a massive star. Throughout its life, the star fuses elements in its core, creating energy that counteracts gravitational pull. Once the fuel runs out, there's no energy pushing outward to balance gravity. The outer layers of the star may explode in a powerful event known as a supernova, leaving behind a dense core. If this core's mass is sufficient, it continues to collapse, leading to the birth of a black hole. Black holes have several key characteristics that set them apart. First, they possess an event horizon, which is the boundary around the black hole. It acts like a point of no return. Once something crosses this threshold, it cannot escape the black hole's pull. This creates a unique environment where space and time behave unusually. Inside the event horizon, the gravitational forces become incredibly strong, influencing the motion of everything nearby. Another notable feature is the singularity found at the center of a black hole. This is where the mass of the black hole is concentrated and the laws of physics as we know them break down. While we can describe many aspects of black holes, the singularity remains one of the biggest mysteries in modern astrophysics. Black holes can vary in size and mass. Stellar black holes formed from collapsing stars and usually contain a few times the mass of our Sun. However, supermassive black holes, which reside at the centers of most galaxies, including our Milky Way, can contain millions or even billions of solar masses. There are also intermediate black holes whose existence is less understood. Understanding black holes not only provides insights into the nature of gravity and space-time, but also enhances our knowledge of the universe's evolution. Every time we study black holes, we uncover new layers of complexity, revealing just how much there is yet to learn about these enigmatic cosmic giants. The event horizon of a black hole serves as a critical boundary that marks the point of no return. Imagine it as a one-way door. Once you cross this threshold, there's no going back. At the event horizon, the gravitational pull of the black hole is so intense that it overcomes the escape velocity, meaning that nothing, not even light, can escape its grasp. This is why black holes appear black. They do not emit light that can reach us. As something approaches this boundary, it undergoes significant changes. For instance, if a star were to fall into a black hole, it would be stretched and compressed due to the difference in gravity between the side nearest to the black hole and the side farther away. This effect is known spaghettification, as the object is pulled into a long, thin shape, like spaghetti. For an outside observer, time seems to behave differently at the event horizon. As an object falls closer, it appears to move more slowly, almost freezing at the edge before gradually fading away from view. This is due to the time distortion caused by the black hole's strong gravitational field, where time stretches out significantly. To the person or object crossing the event horizon, however, they would pass through without noticing anything peculiar, or so it seems, as they would be oblivious to this stretching of time experienced by those outside. Inside the event horizon, the laws of physics, as we understand them, begin to break down, leading to profound mysteries about the nature of reality and the very fabric of the universe. Scientists have developed a variety of innovative methods to study the mysterious realms surrounding black holes. Since we cannot directly observe black holes themselves due to their invisible nature, they focus on the effects these objects have on their surroundings. One primary way is through the study of light. When matter is drawn toward a black hole, it forms a disk that spirals inwards, heating up due to friction and emitting powerful radiation that can be detected by telescopes. This radiation, often in the form of X-rays, provides crucial clues about the black hole's mass, rotation, and the dynamics of the material around it. In addition to light, scientists use gravitational waves, which are ripples in space-time caused by massive objects, especially during dramatic events like black hole collisions. When two black holes merge, they produce these gravitational waves. Detectors around the world can capture these subtle signals. By analyzing them, researchers can glean information about the masses and spins of the merging black holes. Another fascinating approach involves the study of accretion disks. These are the swirling masses of gas and dust that form around a black hole. The properties of these disks reveal significant details. For instance, the speed of the gas can indicate how much mass is being drawn in and help infer the black hole's size and behavior. But finally, scientists are increasingly using computer simulations to model the complex physics around black holes. These simulations replicate the interactions of matter under extreme conditions, allowing researchers to visualize what is happening near a black hole, even if they cannot observe it directly. Together, these methods create a more extensive picture of these enigmatic celestial objects, revealing their secrets bit by bit. The Event Horizon Telescope, a network of radio dishes around the world, made groundbreaking discoveries about black holes by capturing the first image of one in. This monumental achievement focused on the supermassive black hole at the center of our galaxy, known as Sagittarius, us, and another black hole in a distant galaxy called. Prior to this advancement, black holes were primarily theoretical concepts inferred from the effects of their gravity on nearby stars and gas. However, the Event Horizon Telescope provided clear evidence of their existence by imaging the shadow or silhouette of a black hole against the bright backdrop of hot gas swirling around it. This shadow represents the point beyond which nothing can escape the black hole's gravitational pull, giving scientists a visual anchor to study. Additionally, the data collected allowed researchers to confirm that the size of these supermassive black holes aligns with theoretical predictions based on their mass, which is millions or even billions of times that of our Sun. Observations from the telescope also provided insights into the behavior of matter close to the event horizon, helping scientists understand how energy is emitted in the form of powerful jets that can influence galaxies at vast distances. Overall, these discoveries have not only reinforced our understanding of black holes, but also opened new avenues for research into the fundamental nature of gravity and the fabric of space and time itself. The work of the Event Horizon Telescope has marked a significant milestone in astrophysics, bridging the gap between theoretical predictions and observable phenomena in our universe. Black holes have a profound impact on their surrounding environments. They exert an incredible gravitational pull that can attract nearby matter, including gas, dust, and even entire stars. As this material spirals toward the black hole, it forms a disk known as an accretion disk. The intense gravitational force causes this matter to heat up, generating vast amounts of energy that can be emitted as light, often making the black hole visible to us as a bright source in the universe. Furthermore, this gravitational influence can shape the motion of stars and other celestial bodies nearby. Some stars may be pulled into a black hole's grasp, leading to spectacular events when they meet their end. This process can produce powerful explosions that are detectable across vast distances. On a larger scale, black holes can influence the dynamics of entire galaxies. The supermassive black holes at the centers of most galaxies, including our Milky Way, serve as anchors around which stars and other structures orbit. Their presence can affect star formation rates and contribute to the overall evolution of galaxies by heating the surrounding gas and increasing turbulence in the interstellar medium. Black holes can either trigger or suppress the birth of new stars. Moreover, when black holes collide or merge, they can release gravitational waves, ripples in the fabric of space-time, which can be detected across billions of light years and provide valuable information about the nature of the universe. Thus, black holes are not simply dark, isolated phenomena. They are dynamic engines that shape their surroundings in powerful and fascinating ways. Supermassive black holes, often found at the centers of galaxies, play a significant role in shaping the evolution of their host galaxies. Imagine a supermassive black hole as a powerful engine that drives the growth and development of a galaxy over billions of years. When a galaxy forms, it contains a massive amount of gas and dust. The black hole's strong gravitational pull can attract this material, pulling it inward and creating a swirling disk of gas. As this gas spirals into the black hole, it heats up and emits a tremendous amount of energy, often observed as bright radiation. This energy output impacts the surrounding environment. Some of this energy can blow away gas and dust that would otherwise be available to form new stars. This process is known as feedback, and it helps control star formation rates within the galaxy. If the black hole is particularly active, it can prevent the galaxy from creating new stars, limiting its growth and shaping its structure over time. But if the black hole is quieter, more gas can settle into the galaxy, leading to bursts of star formation. Moreover, supermassive black holes can influence the dynamics of the galaxy as a whole. The gravitational forces exerted by the black hole affect the orbits of stars and gas within the central region of the galaxy. This can lead to a more organized structure, helping to stabilize the galaxy's rotation and overall shape. As galaxies collide and merge, supermassive black holes from each merging galaxy can also combine. These interactions can further regulate star formation and even lead to the development of more massive galaxies. Thus, supermassive black holes are not just a curious feature of galaxies, They are central players in the ongoing story of how galaxies evolve and transform across the vastness of space and time. At the heart of a black hole lies a singularity, a point where the laws of physics, as we know them, break down. Current theories propose that this singularity is where all the mass of the black hole is concentrated, creating an infinitely dense point that warps space and time to extreme degrees. According to general relativity, this is a concept in which gravity is so strong that nothing, not even light, can escape. One of the leading ideas about what occurs at the singularity involves quantum mechanics. This branch of physics describes the behavior of very small particles. Merging these two areas, general relativity and quantum mechanics, has proven challenging for scientists. Some theorists suggest that our current understanding of gravity and singularities is incomplete, and that a new unified theory may reveal more about their nature. Another interesting perspective is the idea that the singularity could actually be a region of very high density rather than an infinitely small point. This theoretical approach separates itself from standard interpretations by proposing that the intense gravitational forces might create an environment where space behaves differently, potentially allowing for a multitude of outcomes. Additionally, there are hypotheses about the nature of time itself at the singularity. Some scientists speculate that under extreme conditions, time could behave in unusual ways, even reversing or ceasing to exist. As we understand it, while we have a good grasp of the effects of black holes on their surroundings, the true nature of singularities remains a mystery. As research continues, I'm hopeful that advancements in technology and theoretical physics will reveal more about these enigmatic structures that challenge our comprehension of the universe. Gravitational waves are ripples in the fabric of space-time, created by massive objects moving in extreme ways, particularly during catastrophic events like the collision of black holes. When two black holes spiral toward each other and finally merge, they release enormous amounts of energy, sending out gravitational waves that travel across the universe. These waves carry information about the events that generated them, much like sound waves carry information about a sound source. Scientists use highly sensitive instruments like interferometers to detect these waves as they pass through Earth. When a gravitational wave stretches or compresses space-time, it alters the distances between objects in a very precise way. By measuring these slight changes, researchers can confirm the existence of black holes and glean vital details about their properties, such as their masses and spins. Studying gravitational waves allows scientists to observe black hole interactions and mergers that would otherwise be completely invisible to traditional telescopes. This opens up a new avenue in astrophysics, providing insights into the formation and evolution of black holes and even illuminating aspects of general relativity, the theory that describes gravitation. Thus, through the detection of these waves, we not only confirm the existence of black holes, but also deepen our understanding of how the universe works at its most mysterious and powerful scales. Black holes are pivotal players in the structure of the universe and the cosmic web. Imagine the universe as a vast, intricate web woven from the delicate threads of galaxies and dark matter. Black holes sit at various intersections within this web, influencing their surroundings in powerful ways. At the centers of most large galaxies, including our own Milky Way, reside supermassive black holes. These massive entities can be millions or even billions of times the mass of our Sun. Their gravitational pull is extraordinarily strong, affecting nearby stars and gas. This interaction helps to shape the dynamics of the galaxy, ensuring that stars orbit around the black hole rather than drifting aimlessly. Moreover, black holes can impact the formation and evolution of galaxies. During the early universe, when matter was concentrated in denser regions, black holes likely formed from collapsing stars. As they devoured surrounding material, they released tremendous amounts of energy in the form of radiation. This energy output can heat up nearby gas, influencing star formation. In some cases, it can even suppress the creation of new stars by pushing gas away, creating a balance that helps maintain the structure of the galaxy. On a larger scale, black holes contribute to the cosmic web by helping to shape clusters of galaxies. The gravitational forces they exert can aid in pulling galaxies together, forming clusters that are held in balance by the interplay of gravity and dark matter. The relationship between black holes and galactic structures is both dynamic and essential. They do not merely exist, but play an active role in the evolution of the universe. Additionally, the presence of black holes offers insights into the behavior of matter and the laws of physics under extreme conditions. Their existence challenges our understanding of space and time and raises questions about the fundamental nature of reality. Thus, black holes are not isolated features, but integral components that help define and influence the essence of the cosmos. Black holes stand as extraordinary enigmas in the universe, hinting at the deep laws of physics that govern our reality. They are not just cosmic vacuums. Rather, they are regions where the known rules of physics push against their limits. By studying black holes, scientists can examine the interplay between gravity, space, and time in ways that are otherwise impossible. At the core of a black hole lies a singularity, where matter is compressed to an unimaginably dense point. According to our current understanding, the laws of physics as we know them break down at this point. Investigating these regions can reveal how gravity interacts with the fundamental forces of nature. For example, scientists are eager to understand how the principles of quantum mechanics, the rules that govern the smallest particles, collide with the theories of relativity, which describe the larger structures of the universe. One particularly intriguing aspect of black holes is the information paradox. When something falls into a black hole, it seems that information about that object is lost forever. However, this challenge sparks questions about the nature of information and reality itself. If information cannot be destroyed, what does that mean for our understanding of reality? This paradox encourages scientists to rethink their concepts and may lead to breakthroughs in theoretical physics. Furthermore, black holes can produce waves in the fabric of space-time. These ripples, known as gravitational waves, provide another tool for investigation. When two black holes orbit each other and eventually collide, they release tremendous energy which can be detected across vast distances. Observing these waves allows scientists to gather data about black holes indirectly, enhancing our understanding of their characteristics and behaviors. Black holes serve as a natural laboratory for exploring the fundamental laws of physics. As we uncover their mysteries, we draw closer to a more complete picture of how the universe operates, pushing the boundaries of human knowledge and revealing the deep connections between the very small and the vast. The Great Attractor is a mysterious region of space that has an immense gravitational pull, influencing the motion of galaxies in our cosmic neighborhood. To understand it, imagine a giant magnetic force that draws in everything nearby. This region is located in the direction of the Centaurus constellation, roughly 100 million light-years from Earth. Its exact nature is still somewhat elusive, primarily because it is obscured by the Milky Way's own stars and gas, making direct observations challenging. The discovery of the Great Attractor began in the 1980s, when astronomers noticed that galaxies within our local group were moving towards a particular point in the sky. This unusual movement sparked curiosity among scientists, leading to extensive research. They found that the velocity of several galaxies differed from what would be expected based solely on the observable matter in the universe. This suggested that there was a large unseen force behind these movements. As telescopes became more advanced, astronomers gained a clearer picture of the region. They deduced that the Great Attractor is not a single object, but rather a massive gravitational center formed by a concentration of galaxies, dark matter, and potentially other cosmic structures. Although the Great Attractor itself remains largely hidden from view, its gravitational influence on nearby galaxies allows scientists to infer its presence and importance in the greater cosmic web of the universe. The study of this enigmatic force continues, opening new doors to our understanding of the universe's structure and the forces at work. Within it, the Great Attractor holds a fascinating role in the cosmos as a gravitational anomaly that influences the motion of galaxies in our local region of the universe. Imagine the universe as a vast ocean filled with galaxies. Within this ocean, the Great Attractor acts like a massive underwater current, pulling nearby galaxies toward it with an invisible force. This feature is important for several reasons. First, it reveals the structure and dynamics of our universe on a grand scale. The Great Attractor serves as a center of mass that affects the movement of galaxies, including our own Milky Way, causing them to move towards it. This motion helps astronomers understand how galaxies interact and cluster together, providing insights into the gravitational forces that shape the cosmos. Moreover, the existence of the Great Attractor highlights the distribution of dark matter, an unseen form of matter that, while invisible, exerts a significant gravitational pull. Since we cannot directly observe dark matter, studying the Great Attractor becomes essential to piecing together the complex puzzle of what comprises our universe. Lastly, investigating this cosmic feature helps scientists explore the history of our universe. By examining the pathways and speeds of galaxies drawn toward the Great Attractor, we can glean valuable information about the early universe and how it has evolved over billions of years. Thus, the Great Attractor is not just a curious oddity. It is a key player in the intricate dance of galaxies and a crucial part of understanding our universe's fabric. The Great Attractor is a massive gravitational anomaly that lies in our local universe, influencing the motion of galaxies, including our own Milky Way. Imagine a giant cosmic magnet drawing objects toward it with its immense gravitational pull. This region of space contains a concentration of mass, including clusters of galaxies, and it impacts the trajectories of nearby galaxies as they travel through the universe. As the Milky Way and other galaxies move through space, they do not simply follow a straight path. Instead, they are affected by the gravitational forces of nearby massive structures. The Great Attractor is one such structure. Its gravitational field causes galaxies within a vast area to move towards it. This results in a flow of galaxies, all spiraling toward the center of this gravitational influence. The effect of the Great Attractor is particularly interesting considering the vast distances involved. The Milky Way, along with its neighbor galaxies, is on a journey that leads it closer to the center of the Great Attractor region. It is as if galaxies are in a cosmic dance, with their movements choreographed by the gravitational forces exerted by massive groups of galaxies clustered within the Great Attractor. Moreover, understanding the influence of the Great Attractor offers insights into the large-scale structure of the universe. It reveals how galaxies are not isolated islands, but part of a larger web interconnected through gravitational forces. The ongoing movement of the Milky Way and other galaxies toward this gravitational center is a small glimpse into the dynamic and ever-changing nature of the universe. As we observe these movements, we uncover the intricate relationships between galaxies shaping our understanding of cosmic evolution. The Great Attractor is a massive gravitational anomaly influencing the motion of galaxies across a vast area of space. Observing it presents a unique challenge because of the cosmic foregrounds, such as the Milky Way galaxy, which can obscure our view. To peer through this cosmic clutter, astronomers employ several innovative methods. One primary technique is the use of different wavelengths of light. While visible light can be blocked by dust and gas in our galaxy, instruments designed to detect radio waves, infrared, and X-rays can penetrate these obstacles more effectively. For instance, by observing in infrared, astronomers can see through the dust and identify the stars and galactic structures that lie between us and the Great Attractor. Another crucial method involves mapping the motion of galaxies. By analyzing how distant galaxies move, scientists can infer the gravitational pull of the Great Attractor, even if it isn't directly observable.